Okay, so we're looking at these examples. Laplace transform for the cosine function here. Use your trig identities to express it in terms of sines and cosines. Now, you can put, here's the transform here, and here's the transform here. We apply the transform. Laplace transforms are linear. In other words, the transform function is going to be cosine pi over 3 times the transform of the cosine 3t, and minus the sine pi over 3 times the transform of sine 3t. Okay, so there it is. It's right there using these formulas. We just transform the cosine as a function of time and the sine as a function of time. And these are constants. Cosine pi over 3 is a constant, sine pi over 3 is a constant. Here's another example. So linearity, we just do one at a time. So you have this, by the way, it's making this point, since the integral starts at 0. We have this going on. Delta is just 1, and then you have this for the last integral. And I think they might have a mistake. So now we have, there's a bunch of, it goes through a lot of math now, which I'm not going to do. But I wanted to land on this slide for just a second to show Laplace transform pairs, formulas. Okay. I wanted to stop on this one for just a second too, because it is kind of useful. So we have the function y of t, which gives a transform function this. The derivative of the transform is the transformation of the function t, y of t. So if you want a ramp, this is a good example. You want a triangle instead of a step. So this is going to look like, it's going to look like this. The tu of t. Remember, u is a step function, just steps. Well, this one is a ramp. And we can use the transform of the step function is this. So the transform of the ramp is given by the derivative with respect to time of that. Okay. And then it goes on to more higher derivatives and so forth. So you can show this property. So so do this on your own. I think we've shown enough examples, gone through them in detail enough, you guys can start doing this on your own. Okay, time shifting. So that's when you want to, you have a function that doesn't start exactly at 0. You want to do something a little different. And this is just a change of variables. There we go. To make this identity, to prove this identity. Okay. So you have that kind of thing going on. So you'd have the transform of this. So you have the two step functions. Then the transform is going to be, this is one t naught, this is a second t naught. Just crunch the numbers. It's pretty easy. So I'm going to skip over a lot of these examples. I'm just going to show you the tables. And obviously I got this off Wikipedia of all the different properties. Time domain, this would be the untransformed function. This would be the transform function. Oh, excuse me. This is properties. Properties, not transformations, but ways to manipulate the transformations. Next. This is transformations, common transformations. Okay. Okay. So they're lookup tables. So you've seen going to the inverse transform. A lot of the time, it'll be a proper rational function. Oh, need to turn on my pen. There we go. A lot are rational functions. That's this. Now, we can convert this, find all the poles and zeros of the function, and convert it to a partial fractions. And we know how to do the inverse transforms of this, so we can get the solutions to equations. They can be complex numbers. Poles might be complex numbers. You can use MATLAB to find all the poles, by the way, poles and zeros. Then we put it all together. We have the if you have the same pole several times, the form looks like this. So we can expand it into its partial fractions. We just need to find the k's. And this is the inverse transformation. We come back. So now you've got to find all the k's, go through the math. And we can write the final answer. Okay, gone through one example quickly. Here's something to be good to just spend a second on. If you have complex conjugate poles, you're going to have you can go through, work the complex numbers, and get this answer. Or you can go back and convert this. Come on, pen. You can convert it to the squares and then look up the formula for that, and you get this. You might like it because it avoids complex algebra. Once you get used to complex algebra, it's pretty easy though. Okay. I'm going to go ahead and stop this video here, and I've skipped over a lot of the practices. Do those on your own. Lots of tedious math. Straightforward, but lots of tedious math.